Let's break down the core idea behind this paper, the DeepSeek-V3 technical report from DeepSeek-AI. Look at these benchmark bars. Math, code, reasoning, general knowledge. This open model, DeepSeek-V3, goes toe-to-toe with GPT-4o and Claude 3.5 Sonnet, the best closed models money could buy. Now the part that made everyone sit up, they trained it for about $5.5 million. Not the hundreds of millions you'd guess for a model this size. 671 billion parameters, trained start to finish, and, remarkably, not a single loss spike, not one rollback, the whole way. This video is about the stack of tricks that made a frontier model that cheap and that stable. The first reason it's cheap is that most of the model is asleep at any moment. DeepSeek-V3 is a mixture of experts. Those 671 billion parameters are split into a big crowd of specialist subnetworks, experts. For each token, a little router picks only a handful of them to actually run, about 37 billion parameters worth. So you get the knowledge of a giant model, but you only pay to run a small one on every token. A shared expert always fires for the common stuff. The routed experts handle the specialties. Cheap to train, cheap to serve. But this trick has a nasty failure mode. Here's the failure mode. If the router is left alone, it plays favorites. A few popular experts get swamped with almost every token while the rest sit idle. That's called routing collapse, and it wastes most of your model and jams up the hardware. The classic fix is to add an extra penalty to the loss, an auxiliary loss that punishes imbalance and forces the router to spread tokens out. It works, but it's a bully. That extra loss fights the model's real job of predicting the next token, and quality quietly suffers. DeepSeek-V3's fix is wonderfully sneaky. Drop the auxiliary loss entirely. Instead, give each expert a little bias dial that's added to its routing score, but only for deciding who gets picked, never touching the weights or the gradients. Then run it like a thermostat. After every training step, check each expert's load. If one is overloaded, nudge its dial down a hair. If one is starving, nudge it up. Overloaded experts quietly become less attractive, idle ones more so, and the traffic evens out, all without ever poisoning the learning signal. Balance, for free. The second big saving is raw numerical precision. Normally you train these models in 16-bit numbers. DeepSeek-V3 does most of the heavy matrix multiplies in 8-bit floating point, literally half the bits. That halves the memory and roughly doubles the math throughput. The catch is that 8 bits is a tiny window. Numbers that are too big overflow, numbers too small vanish to zero, and a single outlier value can wreck a whole block. Their answer is fine-grained scaling. Instead of one scale factor for a giant tensor, they chop it into small tiles and blocks and give each its own scale, so every little group of numbers sits right in the sweet spot of the 8-bit range. The running sums are accumulated back up in full precision, and the few most delicate parts of the network are simply kept in higher precision. The result was a first. They showed that FP8 training actually works, stably, on a model this enormous, where everyone else had been too nervous to try. 2 more speedups rounded out. 1. Instead of only ever predicting the very next token, they trained the model to also predict the token after that, with small extra prediction heads chained on. Guessing further ahead is a harder, richer exercise. It wrings more learning out of every token of data, and as a bonus, those extra heads let the finished model draft several tokens at once and run faster. 2. In a mixture of experts spread across many GPUs, tokens are constantly shipped between chips to reach their chosen experts, and normally the GPUs sit idle waiting for that shipping. They design the pipeline so the communication and the computation happen at the same time, hiding almost all of that waiting. Fewer idle chips, lower cost. The 2 headline ideas, in their words. If a frontier model trained for pocket change is the kind of thing that makes your day, like, subscribe, and send it to the friend still quoting $100 million training runs. Add it all up, and the numbers are staggering. 14.8 trillion tokens of training, 2.8 million GPU hours total, around $5.5 million, an order of magnitude below what a model this capable usually costs. The strongest open model of its moment, matching the top closed models on knowledge, math, and code. And the whole marathon ran without a single unrecoverable loss spike or rollback, which, if you've ever babysat a giant training run, is almost the most impressive number on the page. They even distilled reasoning skill from their own R1 model into it afterward. The cost, in one line. So the recipe for a frontier model on a budget: start sparse, a mixture of experts where a router wakes only a sliver of the network per token. Keep those experts balanced with bias dials nudged like thermostats, so you never pay the auxiliary loss tax. Train in 8-bit precision with per tile scaling to have the cost without the numbers blowing up. Predict more than one token ahead to wring extra signal from your data. And overlap the cross-chip chatter with real work so no GPU sits idle. Frontier quality, a tenth of the bill, and not a single rollback. The one-line version, DeepSeek-V3, is a 600 billion parameter mixture of experts that reaches closed model quality for a few $1 million by being sparse, balanced without a penalty, trained in 8 bits, and never wasting a GPU. What I love here is that there's no single silver bullet. It's a dozen careful engineering decisions, each shaving off a bit of cost, stacked until a frontier model fits a startup's budget. The big labs treat that compute bill as a moat. Papers like this one keep quietly showing the moat is mostly cleverness you can copy. That's my read. Tell me yours. Until next time.